Okay, let's continue. So we have seen the significance of the pole, or the poles in the region of convergence, and we have mentioned that if the region of convergence includes the j omega axis, then we say that the system is stable. Let's think of some systems now, and I'm going to show you an example of a system which was originally unstable. Let's assume. Let's say h of t was originally equal to e to the t u of t. Okay, it's an exponential that is growing to the right hand side. What is the Laplace transform of that? That would be h of s. What is it? 1 over s minus 1. And the region of convergence is real part of s is greater than 1. So that's a bad situation. 1 is at the right hand side of the plane, and to the right of it does not include the j omega axis, and obviously this is an unstable system. Interestingly, we have methods to stabilize these things, and in the control systems courses of the next semester, the spring semester, you will probably start with these things. Okay? And it makes use of the linearity property of the Laplace transform. What I mean is this: if you combine two systems, for example, how does the impulse responses behave? If the impulse response is h1, and if you cascade it to another impulse response which is h2 of t, what is the combined impulse response? It's the convolution of h1 of t and h2 of t. But in the Fourier domain, it was h1 of j omega plus h2 of j omega. Times h2 of j omega. And that multiplication comes from the linearity of the Fourier transform, and the same is valid for the Laplace transform as well. So Laplace transform is a linear operator. And why am I telling you this? Because I'm going to use it to do something like this. Suppose your system is here, and the system's Laplace transform is the thing that I write inside. Now there is a very popular and famous way to stabilize some systems. I'm just giving you a glimpse, some hints of how you can use stabilizers. The output here is y of t, and if there's an input, it may be a single, very narrow impulse. Even an impulse will generate a divergent output. It produces e to the minus t u of t. So it's not a stable system. And the popular way to use stabilize this one or such systems is called a feedback. Okay, you may know the name already, a feedback. Now I'm going to use a feedback, and a simple feedback. So the input comes from here. The simple feedback is just a scalar. It multiplies the output signal with k, and it feeds it back to the input by combining with x. So under which values of k, or what region of k, can we make this thing stable? First of all, let's think of the Laplace transform, or the transfer function of the overall system. Can we think of it? Let's write everything in the Laplace domain so that we can multiply with the transfer functions. Otherwise, we have convolutions. Let's forget about convolutions. So the input is x of s, and the output is y of s. And the transfer, or the system we want to stabilize is 1 over s minus 1. Now, y of s is multiplied by k. If the signal itself is multiplied by k, then the Laplace transform is also multiplied by k. It's a linear operation. So k times y of s is combined with our input x of s, and it passes through the system 1 over s minus 1. Okay, it is multiplied by the system to produce y of s, the output. Okay, this is how you can reformulate a feedback system, a simple feedback system. And from here, let's try to isolate y and x to left-hand side and right-hand side, so that we can write y of s over x of s to be equal to the transfer function of the overall system, the dashed bigger system. Let's call it g of s, for example, the combined system. Now k times y of s plus x of s will be equal to s minus 1 times y of s. Let's put k times y of s to the right hand side, and we will have x of s is equal to s y of s minus y of s minus k times y of s, or s minus 1 minus k times y of s is equal to x of s. Now, what is y of s over x of s? It is equal to 1 over s minus 1 minus k. So the previous transfer function was 1 over s minus 1. Now it is 1 over s minus 1 minus k. What is the pole of this? Let's assume k is a real value. Let's forget about the complex values. Where is the pole? The pole is at s is equal to 1 plus k, which means since the original system we assumed to be right-hand sided, causal system in other words. Okay. You remember the causal and such things? The causal systems will have region of convergences to the right-hand side. Clearly. So this is a causal system. So if this one is a causal system, the whole feedback system will still be a causal system. We cannot generate a non-causal system or anti-causal system from a causal system by putting feedbacks and things like that. So I will think of the causal solution. And since this is the pole, and then the causal system will have a real part of S as the region of convergence to be greater than minus 1 plus k. Okay? Is that okay? It's not minus, it is plus, sorry. Just 1 plus k, it's not minus 1 plus k. So real part of S must be greater than 1 plus k. How can we make this thing to include real part of S to be equal to 0 axis, which is the j omega axis? Yes, k must be negative clearly. And in fact, for stability, we must have k to be less than minus 1. Exactly. If it is less than minus 1, for example, if it is minus 2, then 1 plus k will be equal to minus 1. So the pole will be at minus 1, and to the right of minus 1 will clearly include the j omega axis. So strangely, it is possible to stabilize this previously unstable system with an impulse response of e to the t u of t just by putting a feedback by scaling the output with minus 1, with a negative 1. Sometimes control people will prefer to put a minus sign here already. Without a plus sign, they put a minus sign here, which means that it is subtracting the feedback portion from the input. And in that case, k is assumed to be 1, for example, or greater than 1. If k is greater than 1, then with a negative minus sign, it will become stabilized. But if you don't put a minus sign here, then it means k must be greater than minus 1. Then you negate k. You don't negate by putting a minus sign here. You just negate the scale here. Okay? So that's how you stabilize such systems. You can stabilize systems by, some systems at least, by putting a scalar feedback like this, but some systems cannot be stabilized by simple scalar feedbacks. Sometimes you need to put another system, g of s. It may be 1 over s plus a, for example. So should I give it as an exercise to you? This was 1 over s minus 1. And the feedback is 1 over s plus a. The question is, what is the range of A to make the system stable? As you see, I'm not asking for a value of A. I'm asking for a range. It's like this K is, it's like saying K is less than minus 1. A must be greater than something, or in between some values, or less than something. I'm asking for a range. Okay? For some range, the combined system will be a stable system. And what does that mean? It means that the poles will be, the poles of this combined system must be negative. Because it's a causal system. If the poles are negative, if the poles are here, all of them, then a causal system will have the region of convergence to the right of the rightmost pole. Because that will be the intersection of the right-hand side of portions. And if we want to include the j omega axis, then we must have all of our poles to be on the left-hand side, to be negative. So what is the value of A, which makes all the poles of this system to be negative? It may have more than one pole. It may have two poles. Maybe you will see. How can you make them? How can you make all the roots of the denominator to be negative? At least the real parts of them must be negative. Okay, so that is control systems 101. Okay, you are stabilizing by making all the poles to be on the left-hand side of the plane. And sometimes control people are so much accustomed to, used to saying that all the poles must be at the left-hand side, they sometimes miss the concept of region of convergence because they just assume that the system is causal, therefore the region of convergence is to the right-hand side. That's why all the poles must be at the left-hand side, to include the j omega axis. But for us, for signal processing people, it's not, we cannot say that the poles must be at the left-hand side. We must say that the region of convergence must include the j omega axis. Some of the poles may be at the right, at the left, some of them may be at the right, and if their region of convergence intersection is in the center, including the j omega axis, for us it is fine. It is still a stable system. But control system people don't like it because in physics you do not have a non-causal system. The physical systems are already causal. They are always right-hand sided. So they just assume that it's right-hand sided, it's causal, so the poles must be at the left-hand side. That's it. But for our exams, that's not true. You must draw the region of convergence and make sure that the j omega axis is included inside the shaded area of the region of convergence. Okay, now let's see some further examples. Okay. The new example is a signal example like this, and we are looking for the Laplace transform of that. E to the minus 2t u of t minus e to the minus t cosine 3t, now that's a headache, u of t. Now why did I put a cosine there? Just to make the poles and the zeros to be complex. Because previously it was always real. It was minus 2 plus 1, etc. Now we're going to have some complex roots. And the Laplace transform is like this. For the first one, e to the minus 2t u of t, the Laplace transform is clear. It is 1 over s plus 2. The other one, for the other one, let's use the Euler's formula, because then the cosines will be in the form of exponentials, and we already know what the Laplace transforms of exponentials are. So this one is 1 over 2 e to the minus t e to the 3j t plus 1 over 2 e to the minus t e to the minus 3j t in parentheses multiplying a u of t. Good. Now from here we have the Laplace transforms, because e to the minus t e to the 3j t is, or let's write it in even a more compact form, 1 over 2 e to the minus 1 plus 3j t plus 1 over 2 e to the minus parentheses 1 plus 3j t u of t. We can also write it like this. And the first one will have a Laplace transform of 1 over 2, of course, is there. 1 over s minus 1 plus 3j, let's write it like this, plus 1 over 2 1 over s plus 1 plus 3j. Okay. Well, with a minus, unfortunately, it's better to understand. Excuse me about that. Minus 1 minus 3j. I'm going to write it like this. Because they indicate the poles. First of all, we have a pole from here. The pole is at s is equal to 2. There's one pole. Minus 2. Excuse me. Here we have a pole at s is equal to minus 1 plus 3j, and here there's a pole at s is equal to minus 1 minus 3j. Alright. Now where are they? What are they? Let's locate them, plot them on the Laplace plane. One of them is at minus 2, this is minus 2, and the other one is at minus 1 plus 3j and minus 1 minus 3j. Minus 1 is here, minus 1 plus 3j is somewhere here, so here it is 3, it is here minus 1. So we have a pole over there, and we have another pole here where the imaginary axis is this time minus 3. So this is the real axis, this is the imaginary axis. So we have three poles. The poles are, one of them is on the real axis, it is -2, but the other ones are not on the real axis, they are on the plane, somewhere on the plane. A quick hint about this, if the signal is a real signal, of course this one is a real signal. What was the signal? It was e to the -2t v of t, e to the -t cosine 3t v of t. There is nothing complex. It's a real signal. Therefore, the poles and the zeros, by the way, must be in the complex conjugate pair form. The complex conjugation pairs are like this. If within the symmetry of the real axis, if there is a pole at the top, there must be another pole at the bottom with a negative of the other imaginary part. If it is 3j, then there must be -3j as well. They appear in conjugate forms. They must always appear in the form of conjugation like this. So we have these three poles. Let's forget about the zeros for the time being. We will find the zeros as well. What is the region of convergence? As you see, the signal here at the top is a right-hand sided signal. Both for the first and for the second parts, they are right-hand sided signals. So what is the region of convergence? Write it like this. Real part of S is greater than, very well, because it is right-hand sided. What? It's greater than -1. It is greater than, it is to the right of the rightmost pole. So it is to the right of this region. And as you see, the complex parts, the imaginary parts, sorry, of the complex number is not important for the determination of the pole, for the determination of the region of convergence. We don't care about the imaginary parts. It can be -3 or -5 or whatever. We are only interested in the real part of the poles. They are the indicators for the boundaries. And for this case, real part of S is greater than -1 is the region of convergence. By the way, when you combine and make it compact, the Laplace transform, it happens to be, I'm just going to write it, okay? Don't worry about that. 2s squared plus 5s plus 12 divided by s squared plus 2s plus 10 times s plus 2. And as you see, this s plus 2 is the one which induces a real pole at -2. But this second order polynomial produces some complex roots. Those complex roots are -1 -3j and -1 plus 3j. But of course we have some zeros as well. The numerator also happens to contain some zeros. And those zeros are, well, they are quite arbitrary, so let's try not to solve it, but I'm going to show it. They are somewhere here and here in conjugate pairs. It doesn't matter whether they are inside the region of convergence or outside the region of convergence. We don't care. They're just zeros. So this is the pole zero plot of the whole system. And this oscillatory component, the cosine component over there, is an oscillation in the exponent means there is e to the j something. Because that is a sinusoid. You remember that? E to the j omega t is a sinusoid. So if you have a cosine or a sine like that, then the poles do not appear on the real axis. They also have some imaginary components to form e to the j omega things. That is the reason of oscillation. That causes oscillation. So oscillations are caused by putting or inserting poles and zeros, not necessarily along the real axis, but somewhere else in the conjugate pairs, if you insert some poles, then it means you are having some oscillations. You have some cosine terms. Otherwise, you have some real exponentials only. If they are all on the real axis, all the poles are on the real axis, then you have no oscillation. All right. Now another example. These examples I am providing to emphasize several cases of situations in terms of poles and zeros, of course. So we have started by seeing poles along the real axis, and now we have seen off the real axis poles as well. Another situation is when poles and zeros are multiple on the same point. That is also possible. For instance, and there's nothing strange about it, it's just a notation that you need to know. The signal is delta t minus 4 over 3 e to the minus t u of t plus 1/3 e to the 2t u of t. Now, by the way, the last term spoils everything. As you see, it's an increasing exponential towards right-hand side. So I expect that the region of convergence doesn't include the j omega axis. It's not a proper normal signal that we expect for the Fourier transform to exist. It doesn't exist for this one. It must be to the right of some place which is at the right-hand plane, not on the left-hand plane. Whatever. Okay, the Laplace transform of delta we haven't seen yet, but if you just substitute and insert it into the formula, you will see that just like the Fourier transform, the Laplace transform is 1. And the others you know. So the others are 1 minus 4 over 3, 1 over s plus 1, which is the good one, plus 1 over 3, 1 over s minus 2. So the last term, s minus 2, induces a pole at s is equal to plus 2. S minus 2 is equal to 0 point. So s is equal to plus 2 is on the left side plane. Right side plane at 2. And to the right of it will definitely not include the j omega axis. Let's just combine that expression. So this is the Laplace transform, and that is equal to s minus 1 square s plus 1 s minus 2. And the region of convergence is real part of s is greater than 2, which doesn't include the j omega axis. Now, as you see, if you combine something and take the square of it, or cube, whatever, of it, then it means you have multiples of zeros or poles. For this question, we have multiple zeros. The numerator is s minus 1 squared. So where is the pole? Where is the zero of the system? S is equal to 1. S is equal to 1 is a zero of the system. But there are two zeros there. It's not 1 0. There are two zeros at exactly the same position. And the notation of that is not very complicated. Along the real and imaginary axis, let's first indicate the poles. It's at 2 and minus 1. And at 1 we have two zeros. Usually they draw two circles on top of each other like this, just to indicate that there are multiple zeros there. There may be multiple poles as well. Then if you have multiple poles, it's a bit more difficult to indicate them. I prefer to indicate it like this, for example, two crosses very close to each other, something like that. But their numbers, the number of poles and zeros is important because, of course, here it doesn't exist, nothing exists like that. It's just a notation that I'm doing. Because sometimes poles and zeros cancel each other. That's how you eliminate a pole and make it stable, for example. The way to stabilize the system is by eliminating a pole. For example, at s is equal to 2, there is a pole, which is a problem. Then how do you stabilize the system? By inserting a 0 at s is equal to 2. And the 0 in the numerator will cancel the denominator 0. They will just cancel each other in the polynomials. So the pole will be gone and your system may become stable afterwards. So their cancellation is an important issue. Do we have a cancelling example? Yes. Okay. This example is good enough. It's even more than that. It's a very strange example. We will learn many things from this simple example. X of t is equal to, it's a piecewise given signal. Within a region it's equal to e to the minus at, and that region is from 0 to a time, capital T, and it's 0 else. So it's a finite duration signal that we have. Now just a very strong hint. If you have a finite signal, finite duration signal with finite values, the values are also finite, they don't go to infinity in other words. So a very normal signal starts somewhere and ends somewhere. They may be very far away, but let's assume that they stop in certain, they exist only in some certain interval. Then the region of convergence of this signal, the Laplace transform of this signal, is the entire S-plane. The entire S-plane. You don't have any poles to restrict the region of convergence to start from somewhere. Is that true? Let's see for this example. First, let's find the Laplace transform. Let's start from the formula of the Laplace transform. From minus infinity to infinity, x of t times e to the minus st. X of t is e to the minus at, but only within a region, e to the minus st dt. So since e to the minus at is only within a region, it's not from minus infinity to infinity anymore. The integration is within the time limits from 0 to capital T. And I have several lines that I will omit and write the result. The result is this. Okay, it's just calculus, which I'm not very good at. So the integral after evaluation will produce 1 over s plus a, in parentheses 1 minus e to the minus s plus a t. Now as you see, if you just look at it at once, and if I ask you what is the pole of the system, you will tell me the pole is at s is equal to minus a, because s plus a is in the denominator. But there is something wrong, as you may guess, because at s is equal to minus a, e to the minus s plus a times capital T will be e to the 0, because s plus a will be 0. So if s plus a is 0, e to the 0 is 1. 1 minus 1 is 0. So it's a 0 over 0. We are not sure whether s is equal to minus a is a pole or a 0 or nothing. We don't know. It's a 0 over 0 ambiguity. You may immediately consult to the Hospital's rule and differentiate with respect to s whether that s is equal to a is a 0 or a pole or nothing. But before that, and if you do that, by the way, this whole thing, let's give a name. Let's give a name of A, capital A. Well, the derivative, the time derivative of the numerator divided by the time derivative of the denominator will be equal to capital T for this case, if you apply Hospital's rule, which means that s is equal to a is not a pole. And it also says that it's not a 0 either. So what's wrong with it? It looks like the 0 of the numerator and it looks like the 0 of the denominator. This is an example of cancellation, and let's see if we can really have it. So, but of course for that we need to know something else. Now I realize that although I'm giving you this thing as an example for a cancellation, and the result is a cancellation, it's difficult for me to show you how many zeros are there in the numerator and in the denominator, because we need to know something else. Okay, for the time being, let's only say that S is equal to minus A. At this point, we have a pole and a zero, and the number of poles and the zeros is the same. It is 1 for this case. Unfortunately, I'm not able to show you why the number of zeros is equal to 1 for this example. But from the Hospital's rule, at least it's possible to see it this way. It's a cancellation. I'm having difficulty in finding some example questions regarding this one. In the after we see some of the properties, probably we will have some examples regarding that. So I'm leaving that concept, the concept of pole and zero cancellations, in other words, to a future example, because they must appear in the, hopefully they must appear in the examples of Laplace transform properties. So let's continue for the time being. Let's stop it here. The only thing that you have to be careful about is that they may cancel. You may have a pole and you may have a zero, and they may cancel. If the number of poles and the number of zeros at the cancelling point, if their numbers are different, for example, if the number of zeros is 2 and the number of poles is 1, then the poles, then the zeros will beat. They will win, because there are more zeros. There are 2 zeros there, and there are only 1 poles there. It's a situation like this, in short. If x of s is equal to like s minus a to the power 2 divided by s minus b, s minus a. This may happen in the end, after some making compact formula. This may be the situation. And in that case, it looks like there are 2 poles at B and A, and there are 2 zeros at A. So one of the zeros will just cancel with this pole, and it will have only 1 zero at S is equal to A, and it will have 1 pole only at B is equal to B. That's the case, okay? You have to be careful about the cancellations. So you must be good at algebra, okay? Just make a compact form. Yeah. At the top, yes, we can do that, and in fact, they just cancel each other. It's the overall effect is nothing but t times s plus a over s plus a. That's it. They just cancel each other, and it comes from the. For the curious only, okay, you may just close your ears if you don't want to hear what I'm talking about. It's coming from the Taylor expansion of the exponential. And the Taylor expansion of the exponential will have only 1 root at s is equal to a. And that will cancel. The others will be irrelevant. Therefore, that root will cancel with s plus a in the denominator. And we will have nothing. It comes from the Taylor expansion. That's why I just decided not to cover that. Okay? Because it's not as easy as these exponential simple Laplace transforms. Now, we have already seen some examples about both-sided signals, and if you remember, both-sided signals are a bit problematic. Because one of them is going to the right-hand side, the other one is going to the left-hand side. And the intersection will therefore be a strip, because you have a pole somewhere here, let's say to the right. And then you have another pole here to the left. And their intersection will be a strip. Let's see that. A both-sided signal example. X of t is equal to e to the minus b absolute value t. This is not having a u of t or anything. It is to the right and to the left. or you can write it as e to the minus bt u of t plus e to the bt u of minus t. And the Laplace transforms now we can take a look. For the first one is 1 over s plus b, and for this one it is 1 over s minus b. Yeah, exactly. In fact, it's minus 1 over s minus b, but whatever, it's just the scale. So the poles, we will have two poles. One of the poles is at s is equal to minus b, the other one is at s is equal to b. This one is right-hand sided. The other one is left-hand sided. The right-hand sided has a pole at s is equal to minus b. S plus b is 0, so s is equal to minus b. Let's put it here, minus b. And for the other one, s is equal to b is the pole. For this one, it's to the right. For the other one, it is to the left. Therefore, the region of convergence is here. Between minus b and b. Now, very nicely, the Fourier transform exists. Because the j omega axis sits right in between minus b and b. Therefore, we do have a Fourier transform of e to the minus b absolute value of t signal. In fact, we found it already. It's in the tables. You can find it. So the Fourier transform exists. Although it is both-sided, still a very nice signal. As long as minus b is at the left-hand side and plus b is at the right-hand side. As long as. If that is the case, it means b is positive. So that's a signal behaving like this. B is positive, so decaying at both sides. What would happen if B is negative? If B is negative, e to the minus b absolute value of t will be e to the a positive number times absolute value of t, which is a problem. It will grow both sides. Then what will be the region of convergence? Then minus b will not be at the left side anymore because b is already negative. So minus b will be a positive number. It will be somewhere here. And b will be here. So to the right of minus b will be over there. To the left of b will be over there. What's the intersection? Nothing. It's an empty set. So this is valid if b is positive. If b is negative, we have region of convergence to be equal to the empty set. So for a both-sided signal which is increasing with the same rate, both to the right and to the left, increasing with the same rate, you cannot find a suppressing exponential. If you suppress the left-hand side, the right-hand side will grow further. If you suppress the right-hand side, the other side will grow further. So you cannot suppress them equally. You cannot find a proper exponential which just handles the suppression of both sides. This one is a problem. This one is good. Okay? Well, we have several further examples. We can continue tomorrow because then we will see the properties. We will start seeing the properties. So let's stop at this point. We'll continue tomorrow.